So in 4.1, we learned about ratios with rectangles. Well, today we're going to take that up a notch because we're going to deal with ratios with similar triangles. So our focus is for a pair of triangles, if the measure of corresponding angles are equal, how can you use ratios of side lengths to determine whether or not the triangles are similar? Okay, so that's what our focus is today. So again, just to kind of review, with a rectangle, that since all rectangles have four 90-degree angles, you can show that rectangles are similar by comparing side lengths. I'm assuming that's Junique and Curtis. I've never seen that name in my life before, but each have methods that show that the rectangles are similar. Jonique explains that all scale factors between corresponding side lengths are equal for similar rectangles. Okay, and if you look, 2.4, two and a half to three. Your scale factor going from here to here is 1.5. Okay, that's not. And then from 3 1/4. I'm sorry, from 2.5 to 3 3/4. Those are the same sides. Because remember, this is sideways, this is long ways. So these are similar sides here, which you see here. The blue one is right there. Okay. So Curtis says that the rectangles are similar if the ratios have adjacent sides within each shape are proportional. So again, he did the ratio. He did the 9 to the 4.5, right? And the 3 to 1.5. And he got the same ratio. So again, it says you need to compare more than just side lengths of polygons to understand their shapes. In this problem, you will use angle measures and side length ratios to find similar triangles. So let's start applying some of this. So in part A, it says which triangles are similar. Well, there's some missing stuff here, right? Like, for example, we do not know this length, right? How can we figure that out? How can we figure out that missing length for triangle A? You got to think back now when we did this. Yeah, add up the two angles 61 and 30, and then subtract it from 180, right? So if we do that, 61 and 30 is 91, right? 180 minus 91 is what? 89. So 89 is this measure, right? What about for triangle B? It's missing this angle right here. So we got to figure out what that is. Well, again, if I add these two up, I get 105, right? So if I take 180 and subtract 105 from it, what do I get? Yeah, it's 75. What about this one? 89 and 61 is what? Some of you guys got calculators right there. Use them. 150. And if I subtract 150 from 180, okay. And then down here, I got 30 and 89, which is 119. If I subtract 119 from 180, 61. All right, so we found all of our angles, right? So now we have to think, okay, which sides are the same? Because all these are going different directions. Well, this is the base of this triangle, right? So that side should be similar with this side, right? Because if you notice here, are these right angles? How do you know that? Why isn't this angle here a right angle? Blake? It's not 9, it's 89. It's close, but it's not a right angle, right? So which triangles right now do you think are similar? Yeah, you can tell by the angles, right? If you notice all these angles are the same. To B, there's no angles, right? So it's A, C, and D, but there's more than just the angles, right? So our corresponding angles are equal. All right, so let's check out the ratios. Or actually, what if we even scale factor it? So if I take this side, right, smaller to bigger here, so from A to C, it's 4 to 6, right? Scale factor. So we're going up. If we're scaling up, right, it's 6 divided by 4, which is 1.5, right? Right? If I go from C to D, 10 divided by 6 is what? That's a little bigger. 1.6 repeating, I just did 1.7. But now let's go the same side. So this is kind of the 89 side. So if 7 to 10, right, 10.5 divided by 7 is what? 10.5 divided by 7 is 1.5. See the pattern? 12 divided by 8 is 1.5. So these three, this is the same scale factor, right? So when I go from C to D, these aren't going to have the same numbers, 1.7 and 1.5, because these are three different size triangles, right? But if all the sides had the same ratio of scale factor, we're good. So between A and C, we know that's good because the scale factor is constant. So go from C to D. We did the 10 divided by 6. So if this is the 10.5 side, what's the same side as the 10.5 side, Blake? Well, that's a question I'm asking right now. What's the same side as the 10.5 side? Here. Isn't it 17.5? Yeah. So if we take this and do 17.5 over 10.5, hopefully we get the same number. So 17.5 divided by 10.5 is 1.6 repeating. And then if we do 20 divided by 12, hopefully we get the same number. Yep. So from C to D, our scale factor is the same because, again, they're constant, which means the same number keeps showing up. So we know C and D are good. A and C are good. Well, let's go A to D. So 10 divided by 4. 2.5. Right? The 17.5 and 7. 2.5. So it's working out pretty good, isn't it? 20 divided by 8. So again, because this is constant, which means the same number keeps appearing for all three sides, all right? That's how we know that all these triangles are similar. So that means that our scale factor is constant. So the triangles are proportional. Proportional. Meaning the sides are similar, okay? Because they're the same. Because the scale factor is constant, 1.5 for all three sides, 1.7 for all three sides, 2.5 for all three sides. You won't get the same numbers with this guy, so this is kind of the odd man out. So now, this is what I want you guys to work with in your groups right now for a minute. It's part B. So it says for the triangle above, find the ratio of the shortest side to the longest side. Find the ratio of the shortest side to the middle side. The middle side means what? The second longest, right? So if this is, I know this is kind of busy, so let me erase a little bit of this because we did some work here. So if I look at triangle A, what's our second longest side? Blake?
7 meters.
Yeah, right here, right? So that's basically the middle, okay, side, what they're talking about. All right. So I want you to kind of go through and do those two right now. I'll give you 5 minutes. Okay, so you're going to do triangle A, B, C, and D. You're going to do all four that are in this picture. All right. Use your calculators. Remember, you find the ratio from these. This first one. Let me go down a little bit here. So from the shortest side to the longest, and then the shortest to the middle. So shortest to longest will be on the left-hand part. The shortest to the middle will be on the right-hand part. All right. I'll give you guys 5 minutes. We're gonna pause the video. Let's see how you did. So we go down. This is gonna be tough to see. So triangle A, the shortest side is 4. The longest side is 8, right? So if you take 4 and divide it by 8, what do you get? 0.5. Triangle B, the smallest side was 9, and the longest side was 13, right? So when you take 9 and divide it by 13, what do you get? So we'll say 0.69. We'll just, not same number, right? For triangle C, the smallest side was 6, the longest side was 12. So 6 to 12, what's that decimal? 0.5. And then from triangle D, the smallest side was 10, the longest side was 20, which is? So again, if you look, D, C, and A, which we said were similar up top, are the same because those ratios are the same. All right, now let's go to the middle side. So the middle side, or the smallest side in triangle A is 4. The middle side is 7. What's that ratio? 4 divided by 7. Blake? Just go 2 decimal places.
Yes.
4 divided by 7. 0.57. Because it's like 5, 7, 1, 4, 2, 8, da 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 da. All right, so from triangle B, we go, our shortest side is 9, our middle is 12. Well, this is 0.75. Not what we're looking for, right? The numbers are backwards. Don't want that. Okay, triangle C, it's 6 to 10 and a half. What's 6 divided by 10.5? 0.57. So hopefully you're seeing the trend. And then 10 to 17.5 in triangle D, which is 0.57. So again, you can see those ratios are the same, which is why those triangles worked out to be so proportional, which make them similar. All right. I'm going to give you guys another 5 to do the part C. Part C says, and I'm leaving this up for right now because there's still people writing. Use the similar triangles you found in part A, which means A, C, and D, right? Those 3. You're going to find the scale factor from the smaller triangle to the larger triangle. So they want you to go from A to C, A to D, and C to D, which you kind of already did, so this should go fairly quickly. So we'll give you about 3-4 minutes to actually put the work in for those. So you're finding the scale factor, right? Remember, we kind of did that work up here. I'm not going to show it to you for too long. Okay? So we kind of did that work up top. So taking that now, I want you to just do part C. Again, we'll give you 3 to 4 minutes. We're going to pause again. So who remembers the scale factor from triangle A to triangle C? Elena. 1.5, right. And just so you remember, there it was, right? Well, we erased it, right? It was up here, right? All right. What about from A to D? Blake, 2.5. And then from C to D. C to D. Huh? Wasn't 2.5. Yeah, it was 1.6 repeating, or we rounded to 1.7, right? So it says compare the information given by the ratios of the sides in question B to the scale factor in question C. Well, are they the same number? Are the ratios and the scale factor the same number? No, they're different. So the ratios and the scale factor are different. I mean, that's an obvious one. They're not the same number. And then again, remember, the scale factor tells you what? What does a scale factor tell us about the two figures? What does a scale factor tell us about the two figures, Anthony?
Bigger the figure is.
Yeah. How much bigger or smaller the new figure is compared to the original, right? Um, so it tells you how much bigger slash smaller the new figure is. Whether you're going from a little triangle, whether you're going from a little triangle to a big triangle, or so on, right? And then the corresponding ratios. So the ratios of adjacent sides. Now remember, who remembers what the word adjacent means? What are adjacent sides? Blake?
Sides that meet at a vertex.
Yeah, sides that meet at, so in a rectangle, they meet at a point, right? They form a right angle. Or triangle, they meet at a point that form an angle in the triangle, right? So the corresponding ratios of adjacent sides within a triangle, because that was one of the things we were trying to find out, are equal for all similar triangles. So what that sentence means is if the adjacent sides are equal, the triangles are similar. So you'll never have a triangle that the adjacent sides ratios don't match up. And again, if that's the case, that means that then it shows that it's proportional. This shows they are proportional. That's a big word. Proportional. Okay. Everybody got that? All right, let's talk about the summary real quick. So, for triangles to be similar, corresponding angles must be congruent. What does that mean? Congruent. What does this word mean? Equal, the same. And corresponding ratios of adjacent sides within the triangle are the same. Right? We just talked about that. Okay? In similar triangles, all corresponding ratios are equal. Okay? All three sides, when you compare the same side of one triangle to the side of the new one, those ratios should be the same as the medium side and the longer side. Okay? Scale factors can be different from another for different pairs of similar triangles. Right? Remember the ratios were the same, but the scale factors weren't? That's okay. All right? The scale factor indicates the size of the triangle. Again, how many How many times it's bigger or small, right? How many times bigger the new figure will be? And then the ratio of adjacent sides indicate the shape of the triangle. Okay? So that's our summary. So, that's 4.2.